Alright, so this is Physics Lab 4, where we'll be using the energy principle and Newton's second law to predict the motion of an oscillating spring. And my main result that I found was that my model predictions predicted the positions of the experimental data very well. So here's my video that I analyzed, and here are all the points I found once I tracked the video. Here are our relevant physics principles. Here's the energy principle. Delta E equals work of the surroundings, where delta E equals the sum of the kinetic energies, the gravitational potential energy, and the spring potential energy. And their equations are listed here. And work surroundings for this lab will be 0 because we're going to choose our system to be the Earth plus the spring plus the mass. And there are no forces acting on the system outside of the system boundaries, so we're just going to set it equal to 0. F net is found here by assuming that the only two forces acting on the object are the gravitational force and the spring force. So we add those together to find F net, and once we find F net, we can find the final velocity, and this velocity can be used to update the final position of the mass after each time interval. So here are our initial conditions, and then we have three other constants that we have to find. T, which is the period of oscillation, we find by looking at the Y positions, and after three little oscillation periods, we end up at T equals 4.558 seconds. So we divide this by 3 to get T equals 1.519 for our period of oscillation. Once we find this, we can find K, the spring constant, by using this formula, which we found to be 6.878 newtons per meter. And once we find the spring constant, we can find the relaxed length of the spring, L0, which is 0.127 meters. So here's my code where everything happens. Here are all our initial conditions, the mass of the ball, position, velocity, time step, and here are our constants that we found: spring constant, relaxed length of the spring. Here's where we calculate the energies of the ball, and here is where we use F net to update the position of the ball after each time step. And then here we will find delta K, delta U, G, and delta US to graph them and to visualize the energy changes as time goes on. So let's run our program. So we can see here that the blue ball is the model position and the red ball is the experimental position, and as it goes on we can see that the Y positions are very similar to each other. One thing that this model doesn't account for is forces other than the gravitational or the spring force. There may be other forces acting on the ball, such as air resistance, that would alter the net force, but for this lab we can assume that the only forces are the gravitational and the spring force. And then here are our graphs of the energies. The blue one, let's see, the blue one is delta K, delta kinetic energy. The red one is delta spring potential, and the green one is delta gravitational potential. And then the sum of all of our energies is indicated by the yellow line, which is 0. So what does it mean? Is the energy principle satisfied for our system? We can see here that the sum of the energies is 0. So for a bounded closed system such as this one, the sum of the energies will be 0. So the energy principle is satisfied for this lab. So what if we used the X positions to calculate T, the period of oscillation? Well, we have our time after 3 periods is 4.938. So the t for the time for one period is 1.646, and this differs from calculating t using the y positions, because for the x, again, for the x positions are pendulum motion, and the y positions represent spring motion. And we're only interested in the spring motion of the system, not the pendulum motion. So we're going to use the y the y value that we found for t. All right, so that was Physics Lab 4. Hope you enjoyed.